acids and bases unit. To do this review, you might want to have your data booklet handy and a calculator. So I follow the Alberta curriculum. So I use Alberta curriculum's data booklet put out by the government. So that's one I'll be referring to if you hear me refer to some pages. So when we start the equilibrium acids and bases unit, we usually start with the equilibrium part of it and then worry about the acids and bases part in the second half. So what we start with is defining equilibrium. So to start off with, we have that notion of it has to be a closed system. So you can have your system that is in a closed environment. You just don't want to be able to exchange matter with the environment around it. We want properties can be consistent. So like pH, color, things like that, that wants to be consistent. Now this is one that comes up all the time, and this is like the definition of equilibrium. You have equal rates of the forward and reverse reaction. And that's part of what equilibrium is that you can read the reaction going in that forward direction, like we see with this example with chemical equilibria. So we can read the equation going from left to right, so reactants making products, but at the same rate, products will go to the left and make reactants. So this one being chemical equilibria, that means you have a chemical change. So you're actually showing a chemical reaction, and then you have these arrows. So you'll either see the arrows like this, or you'll just see like that one line with the double arrow on each side. You also have a solubility equilibria, and that is just when you're taking a solid, like an ionic compound, and putting it into water. So what the rate that the NaCl, so this is like salt, this is any salt, but this is table salt, goes into water, it will dissolve, changing the state, aqueous. At the same time, those ions that are now present in that solution will find each other, come together, and form this compound. So NaCl is dissolving, and NaCl is in solution coming together to form the compound. So that's also equilibrium. So this is an old diploma question. Taking a look at it, it has a bunch of information about penicillin, and then you have this reaction that's present here. And here it's just telling, or it's an example of showing that you know the definition. So equilibrium occurs when the rate of the forward reaction is, we want to say, equal to the rate of the reverse reaction. What happened here? So let me just get that out. So I was trying to circle D. So D is the answer here. And of course, it doesn't want to work for me right now, and that's okay. We'll fix it. So that answer was D. Moving on to the next one, we have, again, a system. It's in equilibrium. We can tell because one, it says it in the question. The other is those double arrows. This question does look like it's setting up to kind of find a Kc value just by the other pieces of information we have. But because it's asking about empirical evidence to show you that this system is in equilibrium, their empirical evidence would just be color. Okay, so the color would remain constant in this equilibrium system. Now, when we start talking about what side's being favored, then we would take a quick, bigger look at the color, but that's when we're starting to shift our equilibrium. Now, in this old diploma question, which of the following systems could be in equilibrium? So here, hopefully right away we're recognizing that the answer is A, because we have a closed bottle of carbonated water. That means we have a closed system. B, just ruling out the other ones, a block of ice in a glass of water. Well, that can melt, and we can also lose that water to the air as a gas. So this isn't a closed system, so that would not work. And the same explanation would be in C, water boiling in a kettle. As that water boils, it's going to escape the kettle, so that's not an equilibrium system. And the glass of pop, as the pop is sitting out, it is going to lose that carbonate to the air as well, so not a equilibrium system. Now, when we moved into talking about how we can affect equilibrium, we have the scientist Le Chatelier, and he tells us about how we can stress an equilibrium system. And if you stress a system, your equilibrium is going to shift to alleviate that stress. So it will shift in the opposite direction that you apply the stress. So there are 3 stresses that we're going to apply. One is temperature. And so this is when we're adding in energy or we're cooling the system down. Now this is also noted here that this is the only stress that can affect the Kc value. And we'll talk more about Kc afterwards, and I'm sorry. We'll talk more about Kc that equilibrium constant and how we can calculate it, and then we'll look at how temperature can affect it. Then we also have a pressure change. So pressure depends on moles, and this other note here, it only affects gases. So if you have solids or liquids and you have an equilibrium system and you apply a pressure or a volume change, because those two are related, if there's no gases, nothing's going to be affected, and it does depend on moles, and we'll take a look at that. Then you can add or remove concentrations. And then lastly, catalysts come up in this section as well as an extra question. And what you want to realize here is that it will speed up the reaction, but it does not affect equilibrium. So we can bring it in, and when it says speed up the reaction, it means it will speed up the time it takes to get to equilibrium. Now, when we're looking at our equilibrium system, so we have the system up here, we have energy on the product side. So if we were looking at thermochem, we know this reaction is exothermic. And now the question is asking which one of these stresses, or which stresses, would cause the equilibrium to shift towards the products. So we want to see what will shift right. So let's go through the choices. So if you add H2, so if you're putting in H2, you are adding H2 to the system, so you will shift to the right. If you're adding HCl to the system, so we're adding this in, then you shift to the left. So this one would not be included. Number 3, the cooling of the equilibrium system. Sometimes cooling can be a little bit harder. Think of it like concentration. If you added heat in, so we added to this value, you would shift to the left. So instead, if we're going to cool it, we're going to shift to the right. So we're taking heat out, we're going to want to replace that heat. So that will cause a shift to the right. And the last one, an increase in the volume of the container. So we do have all gases, but because we have the same amount of moles on each side, so on the reactant side, you have 2 moles. On the product side, there's a 2 here, you have 2 moles. So a volume or a pressure change would not have any effect on the system. So the answer for this one is A, 1 and 3 only. This next one, we have another example with the system in equilibrium, and this one is asking for the position of the equilibrium to shift towards the products. So we want to shift right again. The pressure of the system should be. So for this one, if it's a pressure change, we do want to look at the number of moles. So like the products on the last question, there's 2 on the right-hand side, and then on the left-hand side, there is 4. Now, what I tend to remember is that if you increase your volume, you move to the side with more moles. And now because we know pressure and volume are indirectly related, or they're inverse to each other, that would mean that pressure had to be decreased. So if I want to shift to the product side and I want to move to the side with less moles, then all of this has to be in reverse. So I would want to increase pressure, decrease volume, and then I would move to the side with less moles. So coming down here, again, don't know why this is so sensitive. So the pressure of the system should be increased. And then it's talking about your temperature. And if we want to inflict a temperature change that will affect the products to shift to the right, we're going to have to take energy out of the system. So here we're going to, just answering the question, pressure of the system should be increased. So we're looking at A or B. And then your temperature should be decreased. So the answer here would be B. This question is still related to the same equation, but this time we're asking about a catalyst added to the system. So we want to remember that a catalyst does nothing. It does not do nothing. It doesn't cause a shift. It just causes us to get to equilibrium quicker. And then it's asking about the delta H of the system. The other thing a catalyst does not affect delta H. So a catalyst has no effect on the overall reaction. It just lets that reaction happen faster. So now coming to this next one, we have the same kind of idea. We want to be able to look at what's happening at our graph. And every Le Chat graph has a particular look to it, or every stress, I should say, on Le Chat. Sorry about that again. So when we're looking at this system, what I like to look at is the lines, and when you're looking at different type of stress, if it is a temperature change, you will have no vertical lines. So because we don't have a vertical line, say just on the first reaction going straight up or straight down, we know it's going to be a temperature change, and that's also because it's on all of these. So no vertical lines. Now what I would want to look at is what way we're going, and this one might not actually have to because there is not an option about temperature being decreased. So it's most likely this one. Let's just double check here. So if a catalyst is added, then nothing would happen. So it would just get to equilibrium faster. So sorry, that was supposed to be an X, not a star. If pressure is decreased, so if your pressure is decreased, you're increasing your volume, you're moving to the side with more moles. And if we were moving to the side with more moles, then that would be the reactant side. So instead of seeing F2 and O2 increasing, like we should, we're seeing it decrease on this graph. So it can't be B. Let's just double check D. Fluorine gas is removed. If fluorine gas was removed, you would see a vertical line going straight down. So that's not implying that. So the last thing we want to check is temperatures increase. So if temperature is increased, you're going to shift to the right. So shifting to the right means you're going to make more of OF2, and that is what the graph is reflecting. And to make more of this, the F2 and the O2 need to be used up, and that is again what the graph is reflecting. So the answer is C. Again, double checking that. Right away we know it's a temperature change because there's no vertical lines, and then you just want to make sure that shift makes sense for your graph. This is another one showing the graph. So we have that reaction. I am sorry. Why isn't it stopping? There we go. So we have our graph, and so I still don't know why the tablet is like that, and I can't figure out why it's so sensitive. Okay, sorry about that. So we're coming here and we're seeing our equilibrium system. Just doesn't like me right now. That's okay. Okay. And looking at this, it's asking which graph represents a change in the equilibrium system at time X when the result is heated. So right away, we know we can rule out B, and that is because we have a vertical line going in the downward direction. Anytime you have a vertical line, it's going to show a pressure change or a concentration change. It's a concentration change if only one line's affected. So with heated, taking a look at our graph, we have our energy on the right-hand side. So if you're heated, you're going to shift to the left. That means the product needs to be used up. So that's going to go down in concentration. And your reactants are going to increase because if you're shifting to the left, you're going to make more of it. So now you just want to see what graph is going to reflect that. So in graph A, we see our reactant being decreased, so that's not going to work. B, we already ruled out. C shows everything increasing, and that's not quite true. And D is showing your reactants increasing and your product decreasing. So your answer here was D. Coming over to our next part here, this is also showing that we do understand how to set up the Casey expression. So what we have here is, it does tell you have NOCl undergoes an endothermic partial decomposition reaction. So we'll have NOCl, and it's going to decompose into NO and Cl2. Now, if this is an equilibrium, that also means, well, it's going to decompose, then your two gases can also come together to form the NOCl. Now, before we do anything else, we do still want to balance this. So because there's 2 chlorine on the left, let's put a 2 in front of our reactant, and that would also make 2 NO on our product side. So coming down, showing the statement, it says reaction representing the forward reaction. So we can get that one quickly. It looks like it's going to be either C or D based on what we have written down. And when you write in your Casey expression, you're always including your gases, your liquids, if everything's liquids, and you keep out solids. So it's always products over reactants. So we'll have Cl2, and then you multiply it by the other product. And if you have a coefficient in front, that becomes the exponent. And then I write down my reactant. I have a coefficient in front, so that will be my exponent. So I come down here, and the one that lines up with that is C. So C was my answer. Now, this is just another shift question, so maybe we'll skip this one for now, just because it's talking about all the shifts, but I think we have reviewed that now. Now, we just showed how to set up the Kc expression, so with using a balanced chemical equation. Now, you also want to understand the Kc values, and the Kc values really range. They can be very, very small to very, very large. In general, what you want to remember, if Kc, or your and K might not just say Kc, it could show Keq, could say Ka, it could say Kb, depending on the reaction. But in general, if it's greater than 1, your products are favored, meaning you have more products than you do reactants. If it's less than 1, you have more reactants than you do products. If it equals to 1, then nothing is favored. Now, what is the only thing that can cause Kc to change? That is temperature. There is nothing else that will affect your Kc expression. So moving on to our next question, which of the changes of the equilibrium system numbered above would affect the value of the equilibrium constant? So again, the only thing that could affect it is temperature, whether it's an increase or a decrease. So the answer is D. Now coming over here, it's actually doing the calculation. So to be able to do a calculation, you need to set up your Kc expression. So again, it's always products. And if you have a coefficient, it becomes your exponent over your reactants. So here we have H2, and here we have I2. I would also just double check that it's balanced. And if you see a coefficient, it most likely is, but just take a look. And this one is, so we'll keep going. And then here it's nice and easy. We just have to do some replacing. So HI is is 1.87. This is in millimoles. So we would, we want to change that to moles. And that, I might do it up here just to show this. So there's 1,000 millimoles in 1 mole. So we're gonna just quickly do those calculations. That's just gonna change where your decimal is. And sorry, I have my calculator right here, 0.87. And I should just be able to do that in my head, but I just want to make sure I don't mess that up. So I'm just going to continue down here. So 0.00187, that value will be squared. And then we'll just keep going here. So you have that 0.057. Sorry, just making sure I was looking at the right thing. So that would give us 5.7 times 10 to the negative 5. So because this is all concentrations when you're putting it in, so those square brackets mean mole per liter. That's why I know I need to change it. And then that last one of the millimoles of I2, 1.07 divided by your 1,000 gives you 0.00107. So now that that's set up, now we can plug that all into our calculator. So we'll take the top value, you'll need to square it, and then we're going to divide it by the two bottom values, but we'll need to multiply them by each other. So I'm getting the value 57, and then I do have a decimal here, but based on sig digs, I'll just keep 2 sig digs, and so that answer is A. So moving on from this one, it's a similar question. We have the balanced chemical equation. They could have asked a question because it is a 2-part question. So the first one was probably how we would affect equilibrium. And then the second one is calculating your Kc value. So same idea as the last question. You want to set up your expression. Make sure to add in those exponents. Keep your units in moles per liter, which they are, so you can directly plug it in and then get your answer. And then another type of question you could see, but same idea, is instead of giving you the values, you have to read the values. So if I were to actually do this one, just because I didn't do the last one, I would make my Kc expression. Again, I have products over reactants. So I have carbon monoxide and then hydrogen gas, and that's to the power of 3. And why does that do it? I'm not sure. Got way ahead here. So I have hydrogen gas to the power of 3. Let's go back there and put that. And then I am dividing by water as a gas, so I can include it, times CH4. Now, why this question is just a little bit harder is because you're not given these actual values at equilibrium, you're given the graph. So from the graph, you want to know that equilibrium is established when your lines are horizontal. So we don't want to read anything from the graph from this part because it won't be accurate. We want it from when it's horizontal. So for instance, your hydrogen gas would be 1.8 and then double check your units, and that is moles per liter. So we'll plug in that value and then you can keep going. So I'll let you finish off this question if you want to, but that is how you would do it. Set up your expression, see where your lines go horizontal, get those values, and then plug it in. So the calculations itself are pretty easy. I think this one's similar, so we'll skip this one as well. The other part is understanding that Kc value. So we talked about that already, but just to talk about it one more time, Kc, if it is greater than 1, products are favored. So when you're looking at comparing, the bigger the number is, the more products you have. Just like if Kc is less than 1, reactants are favored, and then the other part of that would be true. The smaller the value is, the more reactants you would have. So when I'm ordering what would produce the most products, I am looking for the largest Kc value, which would be reaction 2. And then my next largest would be 4, and then I'm getting smaller. So once I cross on over, then I would have 1, and then my most negative or exponent is 3. So that would mean the least amount of products are formed. Now moving on from here, the next part that we start to look at is Bronston and Lowry reactions. I'm sorry about that. So here, we will always want to include an indicator. If you're in Alberta, your indicators that, unless it tells you otherwise, that you would take a look at are on page 10. And then you'd also want to be able to tell what's being favored. So that is all based on location in your data booklet. Again, in Alberta, your data booklet has everything on page, or your acids and bases on page 8 and 9. So based on 8 and 9 and placement of your acid and your base, then you'll know what's being favored. And then this next point here, if it's not in your data booklet, Ka will be given, and from there you would know where to put it in your data booklet because all of your reactions have a Ka value. Then from here, if your acid on your table, so if your acid is higher on your table than your base, products are favored. If the base is higher on the table than the acid, and by your table I'm still talking about page 8 or 9, then your reactants are favored. You also want to know the terms monoproduct and polyproduct. So monoproduct, if you're an acid, you only have 1 hydrogen to donate. If you have more than 1, you can just say poly. If you're a monoproduct base, you can only accept 1 hydrogen. If you're poly, you can take more than 1. Acids always donate protons, and your proton is a hydrogen or a hydrogen ion, and bases accept protons. So looking at our old diploma question here, we have the reaction given, and it's asking the Bronston-Lowry acid in the equilibrium system represented by the equation above is. So again, your acids donate hydrogens to the base. So this polyatomic ion is losing a hydrogen and it's going to the water. So this would be an acid. Water is acting as your base. And then over here, the opposite is happening if we approached it from the product side. So the reverse direction, your hydronium ion is donating a hydrogen to the polyatomic ion. So here we have an acid, here we have a base. So when we're looking at the question, the Bronston-Lowry acid in the equation above, so we want to take a look at, and in this one equation, water can be an acid or a base, but in the equation we're looking at, it's only acting as a base. So it's not going to be water. And acids always donate protons to the base. So here the answer is C. Now, with this next one, we're not given the whole reaction, but you have NH4 positive, and it's mixed in a solution containing HCO3 negative. So when we're taking a look at this, and you can tell from your data booklet that NH4 is an acid. HCO3 is a little bit trickier because it can act as an acid or a base. So here the acid will donate to the HCO3, but this one has to be acting like a base in this reaction. When the NH4 positive loses an acid, loses a hydrogen, when it loses a hydrogen, it will, and I should also show that this can go in both directions, you'll get NH3. And then when your HCO3 negative gains a hydrogen, you'll get H2CO3. Now from here, it says in the forward reaction, so we're reading it from left to right, the Bronston-Lowry base is going to be the HCO3 negative. So not NH4 positive, because that can only act as an acid. And its conjugate acid, Bronston-Lowry base, and its conjugate acid. So a conjugate acid and a conjugate base are different by just one hydrogen. So they're really similar in chemical composition, except in one you just have one hydrogen, and then the other one you have two. So it's a difference of one. So we wouldn't pick this one. So your answer is A. Okay, so this one is a little bit I wouldn't say harder, just a little bit longer. And so we have something that looks like the data booklet. So this is like page 8 and 9 of your data booklet. But most likely you won't find most of these on the data booklet. And why we would know that is because KAs are given. So if you are looking at a reaction that's going to favor your products, you want your acid higher up on your table than your base. Something else you would want to look at is just to make sure your KAs are given from the most positive or the largest to the smallest, which they are. So coming over here, looking at the reactions, I can take a look at the first one. I have this acid here, and I have C2H3O3. So C2H3O3 is here. So here your acid is lower than your base. So that would mean reactants are favored because we need acids higher than your base. So it won't be the first one. So let's keep going. So we have C7H6O3, and then the other one you have C3H5O3. So that's down here. Your acid is higher than your base. So it looks like the answer is B. You might want to just double check the other ones and just a quick scan. Just going to double check that last one on the bottom. C2. Yes, all the other ones had reactants being favored. So your data booklet table works exactly like this, just based on placement. So this is a similar question, so we'll just skip it for now. And same thing with this one. We'll just skip it. Just with this one, note that your KA, and this happens a lot of the times on the Alberta diploma, was not given in order, so check that first. So I like to give this question a lot in class for that reason. So just notice that you're given two reactions. One is in the data booklet and one is not. But if this was in the data booklet, this ion would be lower than the ammonium ion. And so then we could read and answer the question in that way. So moving on from this, we have a solution that's tested and has a pOH of 3.2. If you're better with pH than pOH, just subtract that from 14. So if you did 14 minus 3.2, we're getting 10.8. And then I think it's easier to tell because most students understand the pH scale better than the pOH scale, that your solution is a base. So the solution would most likely be a proton acceptor. So just noticing that if your solution was a base, it would not donate hydrogens, it would accept hydrogens. And then in terms of your indicator, your page in your data booklet, page 10, is all based on pH. So that's another reason why we probably would have wanted to, I am sorry once again, turn that into pH first. Oh, this is pretty far back. There we go. So I'm just taking a look at those two indicators. So thymolphthalein is 10.3. And that would be blue. And then I just want to double check the other one just to make sure. So A looks right. And where is thymol blue? Up there. Oh, okay. And then thymol blue should have been blue, and it says yellow. So that's not true. Okay, so your answer there was A. Now moving on just to conjugates, we did talk about this briefly, but just to re-emphasize that if you have a conjugate acid and a conjugate base, they are right beside each other on the data booklet. In your data booklet, you will see the row conjugate acid with the conjugate base. They are a difference of 1 hydrogen. So we know a conjugate acid with a conjugate base. So looking at this example about ascorbic acid, so taking a look at this just to begin with, oh man, this is so frustrating. Again, I am sorry. Okay, I'll finish off this question and then maybe we can just take a brief break here and I'll start a new PowerPoint. So taking a look at this one here, you have the acid. It's going to donate a hydrogen to the base. And then we have its conjugate base. Now this can continue to donate because you have another hydrogen here. So that is known as amphiprotic. So ascorbic acid is polyprotic because it has more than 1 hydrogen to donate. Its conjugate base is this ion right here, and this ion can be amphiprotic, meaning it can donate and accept a hydrogen. So your answer is C. So we just talked about this definition. So if you're amphiprotic, like water is, the other way, you can donate a hydrogen and you can accept it. It does say what to look for: a hydrogen and a compound that has a negative charge, so an ionic compound. Not ionic, sorry, a polyatomic ion, and then species can be found on both sides in your data booklet. So keep going from here. If we're taking a look, just with that in general, we had, I think it's just doing it more and more. I'm so sorry. Here we go. So we have the one that has a hydrogen and a negative is HSO3 negative. So you can donate a hydrogen and you can also accept a hydrogen, that negative charge. So the answer is A. That was B, just to emphasize, sorry. Coming over here, water can act like an acid or a base. We've seen that before. It's definitely not OH negative. That's a base. Here, there's no hydrogen, so it can't be both. This one has a hydrogen to donate and negative, so number 4. Here, you have a hydrogen and a negative to donate, so V, or negative to accept. And this last one, you have 2 hydrogens to donate, but there's no negative to accept. So the answer was 1, 4, and 5, which is C. Now, when we moved on from here, we would start to look at buffers, and a buffer is a weak acid with its conjugate base. So we looked at what was conjugates to each other, so we're going to continue with that. I'm sorry. And the point of a buffer, how it works, is it can keep a constant pH when a small amount of an acid or base is added. And that acid or base can be strong, so it resists the change of pH. So coming over here when it's saying what 2 things can be combined to form a buffer solution, so it always has to be a weak acid with a conjugate base. So we would not pick 1 or 2 because even the water can act like an acid and a base. OH is strong, so we're not going to choose that. So coming down here, it looks like it's going to be 4 and 5. So just double checking, because we don't have any other acid with this conjugate base other than the top one there. Just double checking. So OCl. Yeah, we don't have the conjugates. Okay, so here it is going to be 4 and 5. So I was just double checking this one. If we had a list that contained HOCl, then that would have been a combination, but we didn't have it. So the only one that would be directly across from each other in the data booklet would be these two. So coming to, or keep going, this is more theory on buffers. So here it's asking what could act like a buffer. So to act like a buffer, you have to have a weak acid with its conjugate base. So anything that's strong, rule out. So solution 1 could not be, because HCl is a strong acid, NaOH is a strong base. Looking at the next one, same idea. This is a strong acid. So as soon as we see something strong, you have to rule it out. This is strong. So coming down here, just making sure that it's a conjugate, you have H3PO4. This ionic compound in solution would have the ion H2PO4 negative. So we're a difference of just 1 hydrogen. So number 4 can be an acid-base pair and act as a buffer. This next one, which of the following rules identify the stronger acid and the side of equilibrium that is favored? So to be the stronger acid, you want to recognize your acids. So here's an acid, right? You can donate a hydrogen. NO2 is a base. There's no hydrogens to donate. Over here, this one is, again, an acid. And your C2H5OCOO negative is a base. So I would take a look at my acids and I would want to find them on the data booklet. So the first one looks like lactic acid and it has Ka value of 1.4 times 10 to the negative 4. So, and then your other acid, HNO2, so taking a look, is a little bit higher up and it has a Ka value of 5.6 times 10 to the negative 4. So nitrous acid is higher on the table than lactic acid, so it is a stronger acid. So we can rule this out. HNO2 is stronger, and because it's stronger and it's on the product side, that means that it could drive the reaction towards reactants. So the answer is B. So whatever side your stronger acid's on will drive the reaction to the opposite side. Moving on from here, we have a question that's now bringing in pH. So we have ammonium solution and we have a concentration of NH3 and we're asked the pH of the system or the fluid. So NH3, if you took a look at that, that is a base. So instead of dealing with Kas, you want to turn your Ka into Kb. To do that, you take 1.0 times 10 to the negative 14, so that's the Ka of water, and divide it by your Ka value. So that will give you Kb. So let's do that first. So 1.0 times 10 to the negative 14, and then we're going to divide it by 5.6 times 10 to the negative 10. So don't round too early. This is going to be 1.785, and this number keeps going, times 10 to the negative 5. So that's your Kb value. Then when we want pH, and this is going to get confusing, we have to find our pOH first. So Kb is going to be your hydroxide ion. Sorry, what's happening here? There's a little bit of a delay. Okay, let's try that again. It's going to be your hydroxide ion squared divided by the concentration of your weak base. Sometimes you'll see this subtracting OH as well, but if you're solving for OH, you could ignore it in the bottom. So now we know this value here. So that Kb value, 1.7, that keeps going, times 10 to the negative 5. and that will equal your OH negative squared divided by 0.15. So let's go ahead and solve for the concentration of OH. So we want to multiply that by 0.15 and then take the square root. So now we'll know that the concentration of the OH ion is 0.00, I'm having trouble seeing it on my calculator, 0.0016, and that number is going to keep going, moles per liter. Then from here, we can find the pOH by taking the negative log of that concentration. So we'll do that in a moment. And then lastly, once we have the pOH, then we can subtract it from 14 to have the pH, and that's what we're solving for. So I'm going to now take the negative log of that answer that we already got, get that, and it's 2.78, and that answer keeps going. So it's 2.786, So you can see that A is a distractor because that is pOH. Now we're going to take 14 and subtract that value, and you'll see 11.21. So your answer is D. And just to remind you about SIGDIGs, this has a significant digits of 2, and when you're solving pH or pOH, you count points after the decimal. So 11.21 also has 2 significant digits. Okay, so this question is similar to the last one, just dealing with Ka, so a little bit different, but same idea. This next one is, again, the similar idea. So I think we'll skip this as well. You just don't have to take it as far, so you're just filling out for hydronium. So if I can get my Ka value of H2SO4, then I'm going to have my concentration of hydronium ion squared divided by your weak acid. Sorry, divided by your weak acid. So it's not hard to solve for. You get your K from the data booklet. You know this value of your weak acid. This was an equal sign, sorry. So we multiply that up, take the square root, you'll have your answer. This next one is more of a theory question. To have the lowest pH means you're closer to 0, and that would mean you are a stronger acid. Why is that happening? So classic, or not classic, constant question. So if you have the lowest pH, you're going to take a look to see which one of these, because they're all the same concentration, has the highest Ka. So I'm just doing a quick glance. So I found HF, it's kind of midway down page 8. Then you have H3PO4, which is higher. So this one would have a lower pH. Gonna keep going. This one's higher. This one's the highest. So D would have the lowest pH. Similar question to the other ones. We've talked about that, so we'll skip that one. This is taking a look at Kb values. Here I would say, if you kind of like pH, turn things into Ka. It's easier to deal with, and we'll skip over that. I think these are all kind of very similar now. Okay, I'm going to stop here because when we move into ICE tables, that gets a lot harder. So, and those questions can be a little bit longer. So let's take a break. Please continue with me. The few things that we're going to have to still review for the equilibrium acids and base unit is definitely ICE tables, which we'll take a look at, and titration curves. So we're almost to the end. Please stay tuned for the next video, and I hope that you found this one helpful so far.